Well, greetings, you dedicated AP Environmental Science students. We are going to zero in today on topics 1.9, 110, and 111, which help us to describe the pathway of energy into and out of living systems, which essentially piggybacks off our last topic 1.8 of primary productivity, photosynthesis, and respiration. It sort of helps us understand the super important process of photosynthesis. So the reading that accompanies this set of notes is the same as the reading that accompanied the last set. So if you've already gotten to pages 72 through 75, no need to reread that. Just pointing out which pages you can find some other perspectives on this information. So we're going to zero in on what energy is, a couple of important laws that govern energy, and then we'll put it back into the context of ecosystems. So let's start first with this idea of potential versus kinetic energy. So energy is what allows objects to move, allows us to power our devices, allows us to warm our climate system, warm your buildings, see things, right? So light is a form of energy. Okay, now we're going to classify energy into essentially two categories. Now, of course, there's electrical, gravitational, mechanical, all other kinds of ways that we sort of classify energy, but all of those fall into one of two categories, potential or kinetic. So potential energy is when matter or an object has the capability of doing work, but it's not currently using the energy potential that it has. So we can think that here in this diagram, the person in the diagram is holding that ball up. Now, that ball has the potential to accelerate toward the ground. There is gravitational potential energy. Okay, a battery that is not currently being used is chemical potential energy, or electrical potential energy in that case too. Okay, so the energy is in the object, potentially could be used, it's just not currently being used. Now, kinetic energy is when that energy is actively moving an object or doing work of some sort. So in this case of the drawing, she lets go of the ball begins to accelerate toward the ground. That potential energy of the ball previously is transforming into kinetic energy of motion. Okay. When you use a battery to actually power your phone or your computer, for example, that potential energy of that battery is transforming into kinetic energy or electrical energy, however the case may be. All right. Now, some important laws that govern the transfer of energy and how much energy is available to us. Number one, you guys have probably heard the first law of thermodynamics, that energy is not created, energy is not destroyed, it's merely changed in form, moved around. What that means is at the inception of the universe, the total amount of energy that was there then is the same as the energy that is here now. It has just been moved around or dispersed or changed from high quality to low quality energy, but the total amount is constant. So energy can be transferred, energy can be stored, or energy can be transformed. Now, second law, and this is the one that really kicks us in the behind in ecosystems and ecology, is this second law of thermodynamics, sometimes referred to as law of entropy. So transfer of energy goes from high concentration to low concentration. So the way to maybe consider that, let's think in terms of heat and something we're familiar with. If it's a hot summer day, so I've got air conditioning keeping the inside of my house comfortably cool, and outside is maybe 20 to 30 degrees warmer than inside my house. If we open windows or open a door, the energy is more highly concentrated outside where it's warmer than it is inside. And so that energy, the heat from the exterior, would move through the open window or through the open door into my home. So going from high to low concentration. Now, if we turn that situation around, however, and it's a winter day, so my heating system is keeping it nice and cozy warm inside my house. Maybe it's 30 to 40 degrees colder outside than inside. If I open my door, I'm not letting cold air into my house. What I'm doing is taking the heat from inside my house and transferring that heat to the outdoors where there's a lower concentration of heat. Okay. And when I'm moving the heat out of my house, the temperature inside my home decreases. Okay. Now, with this law of entropy, so because energy is always sort of moving from a higher concentration to a lower concentration, there's always this dissipation. Okay. So in every energy transfer, every single one, no matter what, there's no such thing as a perfect energy transfer. Some of that energy is always converted to a lower quality, more dispersed, less usable form. Okay? This is the kicker. That's what explains that 10% rule we've been talking about in class. So because of that, because of the 10% rule, because energy always in every single transfer, anytime I try to use energy, some of the potential energy is not used and kept organized. Some of it degrades and becomes dispersed and really just becomes not so usable anymore. Systems can only be sustained. Systems are organized. Okay? Systems require a constant input of high quality energy. So ecosystem-wise, that means we constantly need sunlight, or another way to bring energy into the system, because every time it transfers at every trophic level, some of that energy is degraded to heat, okay, and becomes, while it's the total amount doesn't change, what's usable decreases by about 90% with every single transfer. So we're going to think of energy in terms of quality. High quality energy is chemical energy often, or a star. It can be considered high quality energy. Super high winds, lots of capacity to do work, lots of capacity to put that energy to a specific purpose. That's our high quality energy. Low quality energy, and we often sort of just lump heat, right, of the type that makes things feel warm, okay, as examples of low quality energy. So every time I eat my sandwich at lunch, there's some high quality energy inside the food that I'm eating. Much of that energy from that sandwich, I radiate out of my body as heat into my surroundings. It becomes dispersed and really can't be put to anything useful any longer after that point. Okay, that is that low quality energy. And so second law of thermodynamics is the tendency for high quality energy, with every time it's being used, for some of that to be converted into low quality energy over time. So one last thing we want to talk about, and this is a super, super important. Okay, so do we exchange energy or matter with the rest of the solar system and our universe here on Earth? Okay, so closed systems do not exchange energy with surroundings, and they don't actually exist in nature. Our closest approximation that we're trying to do is maybe like one of your insulated water bottles. The goal of that, and the way it's built and what it's constructed of, is trying to minimize energy transfer. So when you put your ice, water, or whatever inside that insulated water bottle, the goal is that the heat outside of the water bottle is much less able to transfer into your water and warm it up over time. Now, it's not perfectly closed because there's no such thing as a perfect insulator, but a thermos bottle or an insulated water bottle is trying to create a closed system in terms of energy. Now, if I just drink my coffee out of an open coffee mug, there's free exchange of energy. The heat from my coffee fairly quickly dissipates and works its way into the room. Okay? Now, the Earth, as we know, it brings energy in from the sun and radiates heat back out into space. So we are an open system in terms of energy. And thank goodness. Otherwise, we couldn't maintain our systems very long because we need constant input of high quality energy. However, in terms of matter, by and large, the Earth is a closed system, which essentially means the matter we have in front of us on Earth is how much matter we have, and so it constantly cycles. So energy comes in and leaves, matter cycles. Okay, so let's move on to food chains because it's going to get too long if I don't hurry up here. So going back to the 10% rule, we have photosynthesis converts high quality sunlight into chemical energy in food. Okay, that is that input of high quality energy. That chemical energy then transfers from one trophic level to the next. Now, by the way, arrows in our food chain, test question, that represents a transfer of energy. Okay, we're not going to describe that as what eats what. An arrow in a food chain is a transfer of energy. So we know about trophic levels. We know about the 10% rule. So second law of thermodynamics, anytime we transfer energy from one trophic level to the next, up to around 90% of the energy leaves as heat or low quality energy. And that helps us to explain why there's so few organisms when we get 2 to 3 or 4 trophic levels up. So sometimes we will graphically represent the 10% rule in pyramids. So there's what's called a pyramid of energy, which shows the amount of energy at each trophic level. And you'll notice that 10% rule is applying there. For each successive trophic level, 90% of the energy is dispersed or put out into the universe as heat or low quality energy. 10% remains, and so on up. Okay, we could think of it as in terms of just numbers. For every 1,000 grasshoppers, we might expect 100 frogs and 10 snakes. And we could also think of it in terms of biomass. Okay, all of them tell the same story. So, quick clarification though. Those pyramids that we just looked at, these guys right here, those are simplifications. They are ways of estimating the amount of energy, estimating the biomass, estimating how many organisms there might be at each successive trophic level. Okay, it doesn't really capture the complexity of nature. Okay, they're a good model for the trends. They're a good way for understanding why we don't have very many trophic levels. They're a good way for understanding limitations built into our ecosystems caused by fundamental laws of nature. Okay, but because ecosystems really are much more complex than a food chain, right? So this food web you're seeing here is a better indication of the interconnectedness of species in an ecosystem. It's really not quite so simple because a fox, for example, doesn't just eat squirrels. Okay? It might eat mice, it might eat rabbits, it might eat birds, etc. Okay, and so it's feeding off of different types of organisms. In some cases, we have omnivores that are feeding from multiple trophic levels. That sort of complicates that idea of trophic levels and energy a little bit. So just make sure we're understanding that. That takes us to the end